Let's begin with the new chapter, Work and Energy. In Work and Energy, first we will learn to define work. Then we will see how to calculate work done by constant force. We will learn about energy, law of conservation of energy, and in the end conclude the chapter by rate of doing work or power. Now, work. In day-to-day language, we often say that when we study for exams, we do a lot of hard work. Magnitude and dedication in particular work is in common language termed as hard work. But this is not true in the case of science. In scientific definition, the work is defined as the product of the force being applied on an object times the displacement of object due to this force. So the work W is force F into displacement S. The SI unit of work is joules or Newton meter. Force is Newton and displacement S is meters, therefore Newton meter. If the displacement is in the direction of force, work done is said to be positive. What does this mean? It means that suppose this is my object and I am applying a force F in this direction. Now suppose the object is also moving in this direction and displacement is in direction of force, we say the work done is positive. Similarly, if the displacement is in the opposite direction to that of force, the work done is said to be negative. Angle between force and displacement in this case is 180 degrees. So what it means is, I have a block, I apply a force F. But in this case what happens is, that block is moving in backward direction and the displacement is in backward direction. So work is negative times F into S. S is displacement. Now if the displacement and force are perpendicular to each other, the work done is 0. Let's say I am applying a force vertically on the block and the block is moving in the right direction. So this is my displacement direction and this is my force acting on the block. In this case, work done is 0. Moving on, let's look at a question. In this question, a block of mass 3 kg is being moved by the application of force of 5 newtons. Due to this force, the block moves 3 meters in the direction of force applied. Now we have been asked to calculate the work done on the force, the acceleration of the block during this displacement, and time taken during this motion. I have mixed the equations of motion with work and energy to make you understand better how these things are correlated. So initially we will proceed by calculating the work done. So this is my block given of mass 3 kg. The force is applied, say on the right direction, 5 newtons. So work done is force into displacement. It will be positive because the direction of force applied is in the direction of displacement. So this will be 5 into 3, which is 15 Newton meters or 15 joules. Now acceleration is given by force divided by mass, which is 5 divided by 3 meter per second square. Now we have been asked to calculate the time taken during this motion. Also, we have been given that block starts from rest, that is, u is equals to 0. So we will use the equation of motion S equal to ut plus half a t square to compute time. As u is 0, this term goes to 0. Therefore, this implies S is half a t square. Now I will substitute the values of S and a to get time t. S is 3 meters equal to half into 5 by 3 into t square. This implies my t square is 3 into 3 into 2 divided by 5. Hence, t is 3 under root 2 by 5 seconds. So this completes our problem. Now let's look into energy. An object having a capability to do work is said to possess energy. the object which does the work loses energy, and the object which the work is done on gains the energy. For example, an object when raised to a certain height gets the capability to do work. We raise the hammer and hit the nail, causing the nail to drive into the wood. As we raise the hammer, it gains the capability to do work, which is transformed into the nail, which makes it go into the wood. Now, how does an object with energy do work? An object that possesses energy can exert a force on another object. When this happens, energy is transformed from former to the latter. The second object may move as it receives energy and therefore do some work. Thus, the object had a capacity to do work. This implies that any object that possesses energy can do work. The energy possessed by an object is thus measured in terms of its capacity of doing work. The unit of energy therefore is same as that of work, which is joules or Newton meter. Moving on to the next topic, which is forms of energy. Energy can exist in many forms. It can be kinetic energy, potential energy, chemical energy, heat energy, sound energy, light energy, and so on. Kinetic energy is basically related to the motion of the object. The potential energy is related to the height of the object. The chemical energy is related to the chemical composition of the object, and so on. In this chapter, we will discuss only about kinetic energy and potential energy. So what is kinetic energy? Kinetic energy. To understand kinetic energy, let's take the example of wind turbines. Wind produces electricity by making the blades of the turbine rotate. Thus, the motion of wind has some energy associated with it, which is getting converted into the light that we use to glow bulbs at our homes. This energy associated with the motion of some object is known as kinetic energy. Now, any object in motion possesses kinetic energy, which is given by the formula Ke equal to half mv square, where m is the mass of the object and v is the velocity of the object. Now, how do we derive kinetic energy? We know from equations of motion that v square minus u square equals to 2as. This implies S equal to v square minus u square upon 2a. The force acting on the body is mass into acceleration, and the work done is force into displacement. Now I substitute this value of displacement here and the force, which is ma, here. So work done is ma into v square minus u square upon 2a. So a gets cancelled and I get half m v square minus u square. We will here assume that the object starts from rest. Therefore, u is equal to 0. Hence we get work done is half m v square. Now this work done is equal to the change in kinetic energy. Therefore, kinetic energy Ke is half mv square. So this is how we derive the formula for kinetic energy. Now let's look at a question. A body having a mass of 2 kg is moving at 8 meters per second. On applying force, its velocity increases to 10 meters per second. Calculate the work done by this force. So what I will do here is I will calculate the initial kinetic energy, I will calculate the final kinetic energy, and I'll subtract both to get the work done by this force, because work done is equal to change in kinetic energy delta Ke, that is kinetic energy final minus kinetic energy initial. So I will calculate first kinetic energy final. This is half mv square which is half into mass is 2 into 10 square, which is 100 joules. Kinetic energy initial is half mu square, that is half into 2 into 8 square, which is 64 joules. Now work done is delta Ke, as I told here, which is 100 minus 64 joules. This turns out to be 36 joules. Hence, the work done by this force is equal to 36 joules. Now let's move on to potential energy. A spring, when compressed or stretched, returns back to its relaxed position almost instantaneously. This means that some kind of energy is stored in spring, which makes it comes back to its original length. This stored energy is called the potential energy. If the energy is transferred to an object and it doesn't increase its speed, it is stored in the form of potential energy in that object. The potential energy possessed by an object is the energy present in it by the virtue of its position or configuration. Now let's see how potential energy of an object is associated with the height of the object. Potential energy of the object is associated with the height of the object as mgh, where m is the mass of the object, g is the acceleration due to gravity, and h is the height from the surface from where you have to measure the potential energy of the object. Now the important point. Potential energy depends only on the height to which the object is taken and not on the path by which it is taken. So I have considered two examples here. The first one, we directly take it from point A to point B through path 1. In the second case, we take it from point A to point B using a different path, that is path 2. What happens in path 1, I will first describe path 1, as force mg is acting on the block and it is raised to a height h. Therefore work done by the force is mgh, which is also equal to the potential energy of the block. In part 2, what happens is, during the initial vertical rise, the work done is something, let's say mgh1. Now this is some, let's say pe1. Now in this and w1, sorry. So now in the next vertical rise, work done is mgh2, which is pe2. In the third vertical rise, it is w3, that is mgh3, which is pe3. When the object is moved in the right direction, I will change the color and show the right direction, this direction, and this one. The force is acting in the vertical direction and the displacement is perpendicular to it. Therefore, no work is done during these two motions. Only the work done is in this part, which I have denoted by W3, this part, which is W2, and this part, which is W1. Now, the total work done W is W1 plus W2 plus W3, which is mgh1 plus h2 plus h3, which is nothing but mgh. Hence, either you take path 1 or you take path 2, you get the same work done or the potential energy, which is mgh in both the cases. With this, I will end the first part on work and energy, and in the second video I'll continue from here. Thank you.